Okay, let's forge ahead. We were just at this slide, and flange separation is what we're eventually going to get around to, particularly for pressure vessel heads. This is a common configuration, and what you don't want is the high pressure here leaking out that way. That's bad. So that's bad. And the thread is actually fairly flexible. As a matter of fact, it's usually the most flexible thing in the chain. So this is actually flexible slash it's a spring. So if you overpressurize the pressure vessel head, you will unload that spring and vent your high pressure out. Now, the one other thing to note here is that you see that they have this thing called L right here. Get rid of some of that stuff. That only part of the thread contributes to the effective grip, L. And you notice they cut it at the first 3 threads. That's pretty much it. You could have 20 inches of thread, it doesn't matter. It's the first 3 threads that really matter. There's a couple graphics in the book. One is for a bolt sunk into another piece of material, and then there's one with a nut. So both of them have a definition of the grip length. So we're talking about grip length here, and grip length is down here. That's the effective grip length. All the rest of this is doing nothing. So delete that. So everything beyond the grip length really isn't doing much for you. That's the essence of this slide. We're going to go through things like bolted joint stiffnesses, also like bolt stiffness, member stiffness. We're about to embark on a bunch of stuff, and there's actually one thing at the end that's the most important that I want you to concentrate on, is when does the flange actually separate? When do you lose clamping? So what we're really looking for here is at this interface right here, we're really talking about loss of clamping. What's really all we're interested in is when does the load exceed the clamping capability of the bolt. So if you look at this, we have the a spring that corresponds to the clamp members, and a spring that corresponds to the bolt. Actually, those are backwards. This is the bolt. This is the clamped members. And when you clamp them together, you get 2 springs. and they're two springs in parallel. So even though one's in tension, and this one will be in compression, when you add them together, the bolt and the actual thing that it's clamping act like two springs in parallel. So here's the one of the graphics in the book. Let me flip in the book to this regarding bolt stiffness. This being bolt stiffness right here. They've got all the definitions on this figure. So here's the definitions. And then here's the salient formula for what the actual bolt stiffness is. This is a two different configurations. This is for a bolt with a nut and a bolt sunk into the flange. So this is two different configurations. And this basically defines like your grip length. Like this would be threaded length, your grip, all sorts of stuff like that, your overall lengths. And then we have threaded length definitions, and then essentially what you're getting down to is fastener stiffness based on those. So you want to determine, are you in this configuration or that configuration, and based on the configuration, define your various. So these various terms are based on the configuration. Then there's member stiffness. This frustum angle here, alpha, I'd like to mention. So while your bolt is in tension, your clamped pieces are in compression. This is a bunch of derivation we really don't need to know about. So this is not particularly helpful, but we'll get to some formulas that'll help you. All this sort of stuff, not really too interested in this. I'll put OK. This is what we're going to focus on. Common material in the grip, like two pieces of steel clamped together, two pieces of aluminum. That's generally what you're going to have. If they're all the same material, then this calculation becomes much more simple, and we can just say that the member stiffness is, according to this formula, 822. And if you have something more complicated, then you probably need to use SolidWorks simulation or some other FEA code. So this is an OK simplification. And again, we can get our approximate member stiffness from this. Why do we need member stiffness? Bolt stiffness. So KB equals K. Sorry about that. Why do we want KB and KM? Why are we even talking about it? K sub B is the bolt stiffness. K sub M is the member stiffness. The member stiffness is the stiffness of things being clamped together. Well, we want that to know eventually whether or not our bolted connection will separate. And then, the book kind of migrates into some other things as a side project, which is a little bit annoying to me because we just got into member stiffness. And let's see where bolt stiffness is. Bolt stiffness. So we had bolt stiffness, then we had member stiffness, and then they go into bolt materials and other definitions, which is really not helpful because the whole reason we wanted K sub B and K sub M is for a completely different reason than bolt materials. But okay, so because the book kind of follows this trajectory, let's get into bolt materials, and then we'll get back to, so we'll have to get back to K sub B and K sub M. Those are actually meaningful. But in the meantime, there's bolt materials. So these are some terms that you should be familiar with: proof load, proof strength, and yield strength. So the proof load is the maximum load that a bolt can withstand without acquiring a permanent set. Generally, bolts are loaded to their proof load. So this is proof load is so or within, I would say, whoops. Within 95% or so. So, like, generally, bolts are loaded properly almost up to their proof load. So, proof strength, this proof strength corresponds to the proportional limit. It's slightly lower than the yield strength, and you generally, we're about 75% of that. If you're loading up a bolt that far, which is probably about where it should be loaded, you probably don't want to reuse it. If you're going to reuse a bolt, definitely back off on that. And if you ever hit the yield strength on a bolt, it's definitely done, and it's not doing anything for you anymore anyhow. So don't yield your bolts. Bolt specifications. This one, if you've been in industry, this seems like almost comical, like simplified, but you have your nominal diameter, threads per inch, length, thread series, class, fit, material grade, head type. Usually you just see something that says quarter, oops, sorry, I'm not quite sure what's going on. Quarter 20 UNC. If you put that down on a drawing, everybody will know what it is. All the rest of it, I'm not quite sure if you've ever seen that on a drawing. I never have. Or quarter 28 UNF would be another thing. That's typical stuff that you'd see. And I've never actually interacted with metric units, so I'm sure these other things down at the bottom of the page are quite fine, but typically what you'll see in the United States here is inches, threads per inch, length, and then what grade it is. And that's generally what you'll see. So now we're getting back to tension-loaded bolted joints. We have a couple definitions here. FI is preload. All this other stuff. This is the resultant bolt load, member load, and then this thing called C, which is the fraction of external load P carried by the bolt. And really, you can just kind of skip all this. What we really need here is C, and that is determined by the bolt and the member stiffness. So that was the whole point of the bolt and member stiffness. And I don't think this is actually I'm not sure if this is in the book. But this is the whole point of this, is that you can determine the separation load based on the initial tension in the bolt and the ratio of the stiffnesses of the bolt and the members to determine the separation load. So I would make sure that you have this written down somewhere for the final exam. I don't think this is in the book, but this is extraordinarily important. This is basically defining the loss of clamping load, P naught. And I've skipped the derivation. This is basically it. You have the initial tension in the bolt, and you have the 1 minus the, let's see what C is, the ratio of KB over KB plus M, and from that you can predict the loss of clamping load. So when are we actually going to separate? Last part of this chapter is relating bolt torque to bolt tension. This is what you need to know right here. There's this nebulous K, which is treated over here in this table. Anything not treated in the table, use K equals 0.2. And that's pretty much it. Make sure you go through examples 1 through 4 in this chapter. And that's the end of what you need to know for this chapter. I'm still getting used to online lectures here, so bear with me. Hopefully I'll do better next time. And there's a couple websites here in case you're interested, or actually just one. It's pretty interesting. And it's an online bolted joint analysis summary. And check it out. You'll see some stuff that's not in the book, and hopefully you find it interesting.